So this problem is about to discuss conversions or diversions of the series sine of 1 plus 1 over n to the power n minus a minus b over n from 1 to infinity. Of course, the discussion here will depend on a and b. So here we are assuming that a and b are arbitrary numbers. So let me recall some of the stuff that I'm going to need. This is a very, very, very hard problem. This is beyond the average calculus series where it's just straightforward calculations. This is a little bit tedious and needs a little bit deeper knowledge of calculus. First of all, let us recall some of the limits, okay, that are non-classical limits. So we know, we have seen it on these pages as well, that 1 plus k over n to the power n, when n goes to infinity, the limit is e to the power k. So in particular, the limit of 1 plus 1 over n to the power n is equal to a when n it's equal to e when n goes to infinity, or e to the power 1. So since sine is continuous, then we know that the limit of sine of 1 plus 1 over n to the power n when n goes to infinity equals to sine of e. So if a is different from sine of e, then the limit of this expression here, all this expression here, will be not equal to 0, because the first one will go to sine of e minus a, b over n goes to 0, so it's going to be sine of e minus a, so it's not equal to 0. So in this case, by the nth term test, we know that the series will be divergent. The series sine of 1 plus 1 over n to the power n minus a minus b over n is divergent, because the n terms does not go to infinity. So in order for us to expect some kind of convergence, we have to assume that a is equal to sine of e. So what happened then? Okay, if a is equal to sine of e. So basically what we have is to look at sine of 1 plus 1 over n to the power n minus sine of e minus b over n, right? So in this case, as you can see here, because of this term, we're going to try to use the Taylor polynomial of sine at e. So we know that, again, recall from calculus, that sine of x is equal to sine of e. This is Taylor polynomial at e, plus the derivative of sine, which is cosine of e times x minus e, plus the second derivative of sine, which is minus sine of e over 2 factorial times x minus e squared, etc. Okay? So if I need more term, I'll come back to this Taylor approximation or Taylor series and then add more terms. Okay? So we'll see. So here, basically, applying this will give us, now we have to be careful, 1 plus 1 over n to the power n minus sine of e plus cosine of e times 1 plus 1 over n to the power n minus e minus sine of e over 2 factorial times 1 plus 1 over n minus e squared, etc. So the next one will be a third power. Huh? So now we are down to see what is 1 plus 1 over n, which we know it converges to e equal to, okay? And for that, we're going to use, we can use the binomial formula, okay? But let's use e and ln for the sake of, okay? So this is en ln of 1 plus 1 over n, okay? And this, what we're going to do we're going to look at the n ln of 1 plus 1 over n. Again, here we use the Taylor polynomial or Taylor series for 1 plus x. We know this is equal to x minus x squared over 2, x3 over 3, etc. So this tells me that ln of 1 plus 1 over n equals 1 over n minus 1 over 2, 1 over n squared plus 1 over 3, 1 over n cubed, etc. So if I take n ln of 1 plus 1 over n, this will give me 1 minus 1 over 2n plus 1 over 3n squared, etc. The next one will be on 1 over n cubed, okay? So if I take now en ln of 1 plus 1 over n, this will be e 1 minus 1 over 2n plus 1 over 3n squared, etc. Use the properties of e, so this is e to the power 1, e minus 1 over 2n plus 1 over 3n squared, etc. We can use the London notation and put here that it is small o of 1 over n squared, but let's move on anyway. So now we have to use the power series of ex again. So this is 1 plus x squared over 2 factorial, etc. So this tells me that en ln of 1 plus 1 over n is equal to e time 1 plus minus 1 over 2n plus 1 over 3n squared, etc. plus 1 over 2 factorial, and then you have the expression squared, 3n squared, etc. squared, etc. So this will be e time 1, and then we have minus 1 over 2n plus 1 over 3n squared. And whatever comes after the n squared, 1 over n squared, will not write it. That's the little o of 1 over n squared. And then here, plus 1 over 2 factorial. And here, this square here gives us only the first term, this one here, the square of that one. So which will be 1 over 4 n squared plus etc. That's the only term that we get. Otherwise, we'll get a higher powers of 1 over n. So this will give me e 1 minus 1 over 2n plus 1 over 3 plus 1 over 8, 1 over n squared, etc. So this, once I put all the stuff together, is e over 2n plus 1/3 plus 1 over 8, that's 11 over 24. So it's 11 e over 24, 1 over n squared, etc. So this is e of n ln of 1 plus 1 over n. So if we go back, which is 1 plus 1 over n to the power n. Okay, so now we go back to our series. So we have sine of 1 plus 1 over n to the power n. So we said this is sine of e plus cosine of e, and then we have 1 plus 1 over n to the power n minus e minus sine of e over 2 factorial time 1 plus 1 over n to the power n minus e squared, etc. So the sine of 1 plus 1 over n to the power n equal sine of e plus, so here cosine of e, and then what do we have now? If we take, we found it, so this is this here minus e. So we get minus e over 2n plus 11 over 24, 1 over n squared. I will stop at 1 over n squared, okay? So the next one will be minus sine of e over 2, and then we have the difference squared. So it's this term here squared. So we only keep the e squared over 4n squared plus etc. Okay, because we're stopping at 1 over n squared. So now this gives me, putting the stuff together, sine of e minus e cosine of e over 2n. And then we have, okay, this expression time 1 over n squared. So what's the expression? We have 11 over 24 cosine of e, because this will give me 1 over n squared, is right here. And then we have minus e squared sine of e over 8. So this is now sine of 1 plus 1 over n to the power n. So if we take sine, so if a, we know that a is equal to sine of e. So here we get sine of 1 plus 1 over n minus sine of e minus b over n. That was the original series. So the sine of e will cancel, and we're going to have minus e cosine of e over 2 plus b 1 over n plus the next term, okay, the next term, which is 11 over 24 cosine of e minus e squared sine of e over 8 times 1 over n squared, etc. So if b is not equal to minus e cosine of e over 2, then we have sine of 1 over plus 1 over n to the power n, I forgot an n here, minus sine of e minus b over n will be equivalent to minus e cosine of e plus b over 2 1 over n. So keep in mind that when n is large, since this one here, this term is not equal to 0, okay, then either it's going to be positive or negative, so we can use the limit test. And since 1 over n, the series 1 over n by the p-test is divergent, we conclude that, so here is a combination of p-test and limit test. But be careful, the limit test, you have to make sure that your series is either always positive or negative after, of course, a certain n, okay? So we get that sigma of sine 1 plus 1 over n to the power n minus sine of e minus b over n, and from 1 to infinity is divergent. So finally, if b is equal to minus e cosine of e over 2, then our term sigma, sine of 1 plus 1 over n to the power n minus sine of e plus e cosine of e over 2n will be equal to, okay, this term here, this one here. So it's going to be a number, so it's going to be a number c over n squared plus etc., where c is not equal to 0. Okay? In any case, this will be absolutely convergent because, again, as we said, this will tell us that the series to the right-hand side, the sequence to the right-hand side, start with 1 over n squared, and the rest are even bigger power than 1 over n squared. So the p-test, limit test, and p-test will tell us that in this case the series is convergent. Sigma of sine 1 plus 1 over n to the power n minus sine of e plus e cosine of e over 2n is convergent.